Welcome back to our data analytics series. Today, we're taking a deeper dive into two of the most widely used machine learning models in data analytics, decision trees and random forests. By the end of this video, you'll understand how to build these models from scratch, apply them to real-world data, and evaluate their performance using various metrics. Let's get started. We will be looking at the following contents in this video. Decision trees and random forests are part of the supervised learning family, used for both classification and regression tasks. While a decision tree is a single tree structure that splits data into subsets based on feature values, random forests combine multiple decision trees to form an ensemble, offering better accuracy and reduced overfitting. A decision tree is a flowchart-like structure where data is split at each node based on the values of its features. Each internal node represents a feature, each branch represents a decision, and each leaf node represents the final outcome, which could be a class label in classification or a numerical value in regression. The process of building a decision tree can be broken down into three major steps. First, we select the best feature to split the data, based on criteria like information gain or Gini index. Next, we create branches for each possible value of the chosen feature, and the data is split accordingly. This process is repeated recursively until either all leaf nodes are pure, that is only one class in the node, or a stopping condition is met, such as a maximum tree depth. It's important to understand some key terms associated with decision trees. The root node is the starting point, where the first split happens. Internal nodes are where additional splits occur based on feature values. Leaf nodes represent the final predictions made by the model. We often use metrics like Gini index or information gain to determine the best feature to split on. Information gain measures the reduction in entropy after split, while the Gini index is a measure of impurity in the node. Decision trees come with a set of pros and cons. They are easy to interpret and visualize, making them ideal for understanding the decision-making process. Moreover, they can handle both numerical and categorical data. However, decision trees are prone to overfitting, especially when they grow deep, and they can be unstable, meaning small changes in the data can lead to completely different trees. Decision trees are applied in various industries. In healthcare, they assist in diagnosing diseases by classifying patients based on symptoms. Businesses use them for customer segmentation, categorizing customers based on their purchasing habits. In finance, they help with credit scoring, predicting the likelihood of loan defaults based on financial features. Let's apply a decision tree to a real-world dataset and predict whether a customer will default on a loan. We'll use a dataset containing features like the customer's income, loan amount, and credit history. Our goal is to build a classification model where 1 represents default and 0 represents no default. We will be working on this file, and our dataset is already loaded here. We start by importing the necessary libraries. Pandas is used for data manipulation, scikit-learn provides the tools for building our decision tree and evaluating its performance. Next, we load the loan dataset and split it into features and target variables. Our features include the customer's income, loan amount, and credit history, and our target variable is whether the customer defaulted. We then split the dataset into training and test sets to evaluate our model's performance on unseen data. Now, we initialize the decision tree classifier and train it using the training data. The model will learn patterns from the data to classify whether a customer will default or not. We now make predictions on the test set and evaluate the model. Accuracy will tell us the percentage of correctly classified examples. The classification report provides detailed metrics like precision and recall, and the confusion matrix helps us understand how many true positives, true negatives, false positives, and false negatives the model produced. And here got predicted model evaluation results. Random forests are ensemble models that combine the predictions of multiple decision trees to create a more robust and accurate model. Each tree is trained on a random subset of the data, and the final prediction is made based on the majority vote of all trees. This reduces overfitting and increases generalization, making random forests a powerful tool in data analytics. The random forest algorithm involves several key steps. First, a random subset of data is selected to train each tree. Then, at each node, a random subset of features is used to determine the best split. Each tree is grown to its maximum depth, and finally, the predictions of all trees are aggregated to make a final prediction, whether by majority vote for classification tasks or averaging for regression tasks. Random forests offer several advantages, such as reducing overfitting and being able to handle large datasets with higher accuracy. They're also robust to noisy data. However, they can be computationally expensive due to the training of multiple trees, and they're harder to interpret than a single decision tree. Random forests are applied in a wide range of industries. For example, in fraud detection, they help identify fraudulent transactions based on patterns in the data. In healthcare, they predict patient outcomes by analyzing medical records. In marketing, random forests are used to predict customer behavior, helping businesses make data-driven decisions. Now, let's build a random forest model to solve the same loan default problem. We'll use the same dataset and features, but train a random forest model instead of a single decision tree. We will work with the same loan dataset, and here, we initialize the random forest classifier with 100 decision trees and train it using the same training data. The model will learn from multiple trees, making it more accurate and robust than a single decision tree. Finally, we use the random forest model to make predictions on the test data and evaluate its performance. Similar to the decision tree, we calculate accuracy, precision, recall, and check the confusion matrix to assess how well the model has performed. To improve the performance of decision trees and random forests, we can tune several hyperparameters. For decision trees, you can limit the maximum depth of the tree to prevent overfitting. For random forests, increasing the number of trees usually leads to better results, but it comes at the cost of computation time. Other important parameters include the minimum number of samples required to split a node and the maximum number of features considered at each split. To evaluate decision trees and random forests, we use several metrics. Accuracy is the overall correctness of the model, while precision and recall focus on specific types of classification errors. The F1 score balances precision and recall, and the AU0C curve provides a graphical representation of the model's ability to distinguish between classes, giving insight into how well the model performs across all thresholds. You've successfully learned about decision trees and random forests, two powerful tools in the data analytics toolkit. In the next video, we'll explore even more about data analysis. See you in the next video.